All right, so our objective today, we have a couple of them. Number one, we're going to understand how to solve one variable motion problems. So these are different than the ones that we did before where we had two speeds working together or opposite each other in order to have some function going. And so today it's just going to be about people driving, walking, bike riding, but it's not going to be where there's an effect of the wind and the water is something we're concerned about. Okay, the other thing we're going to do is to review the distance formula because there is motion going on, and anytime we involve distance, we're involving a speed, a rate, and a time. So this is going to be part of all of our problems that we're going to work on for today and tomorrow. D equals RT. Now I'm hoping that we're going to be able to get through 3 problems today. And then what I was thinking is once I get home later on, I will probably do a second video of other problems so you have more at your disposal to look at. Matthew N.
Are wind and current problems going to be on the next test?
They're going to be on your placement test, and they could show up at any time for any reason. Once we've touched something, we don't walk away. It's always going to be available as a possible answer. Sarah.
Is this still chapter 5?
This is still chapter 5 that we're in. You will see when we talk about the other set of word problems on Wednesday, it's a little bit, deals more with exponents. Okay, this one is just kind of a random weird one, but we've always kind of done them together. So here we go. There's 2 possibilities in motion problems. And when I'm saying motion problems, notice that I'm not saying wind and water current problems. So these are completely different types of motion problems. But these are the type of problems when you say, somebody says, oh, what math class you're in, and you say algebra, instantly they go back, 2 planes leave from the airport at the same time going in opposite directions. How many hours will it be before they're exactly 325 miles apart? And they stop. That is the stereotypical algebra problem people think about, and that's exactly what we're talking about today. Okay? So the 2 possibilities that show up in these types of problems is the distances, and it just usually involves 2 people or 2 objects. The people/objects. Travel is the same. When that's the scenario in the problem, what you're going to do is, using the distance formula, figure out the distance of one and set it equal to the distance of the other guy. So you're going to take the 2 distances and you're going to set them equal to each other. Okay? That's situation 1 that could arise. Situation 2 is the distances add to equal some total distance given in the problem. So there will literally be a number that has a distance label in it, and it's basically saying this is how far apart these 2 are. Okay? So with this, we would say the distance of one plus the distance of the other is going to be equal to this total distance that's you're given in the problem. Okay. So one of the things that we need to do to help us is definitely a chart, because we generally have 2 things that are in motion. Those motions have rates and times and a distance. And so to keep it all straight, that's when we're using our chart. So we can use a chart to organize data. Now, while in the chart, there is no equation that comes out of it, it does have the parts that I am going to use in the equation. How I write my equation is based on D1 equals D2 or D1 plus D2 equals D total. So use a chart and draw a diagram. So that's something we haven't done a lot of. So this really helps because the diagram helps me to see if it's the two distances are the same or the two distances add up to equal some other distance given in the problem. Okay, so I'm going to demonstrate how to do the diagram and then take the data from the diagram, put it in the chart, take the chart, write my equation based on which situation it is, and then solve the problem out. Okay? All right, everybody good here? Can I move on? Yes, yes, yes. What are you talking about? Add to equal some total distance given in the problem. All right, so here we go. And these are lengthy because they're trying to give you a lot of information. So directions are going to just say solve, and here comes the first one. So Mr. Jones left Elmsville at 8 a.m. and drove to Bond City at a rate of 50 kilometers per hour. A lot of data in that one sentence. There's a lot of things going on. He leaves one place, ends up at another place. We know when he left. We know how fast he's going. Okay? At 10 a.m., the same day, so just 2 hours later, Sergeant Holliday left Elmsville. So he left from the same place that Jones did. Following the same route, he arrived in Bond City at the same time as Mr. Jones. If both men arrived in Bond City at 3 p.m., at what rate had Sergeant Holliday traveled? A lot of information. Mr. Jones left Elmsville at 8 a.m. and drove to Bond City at a rate of 50 kilometers per hour. At 10 a.m. the same day, Sergeant Holliday left Elmsville. Following the same route, he arrived in Bond City at the same time as Mr. Jones. If both men arrived in Bond City at 3 p.m., at what rate had Sergeant Holliday traveled? Same is what I kept hearing. All right, there's so many things in here. First thing I'm going to do is draw a diagram of it because I want to figure out, are the distances the same or do the two distances add up to equal something else? So the two main spots are Elmsville and Bond City. Oops. Elmsville, Bond City. We have Mr. Jones. They tell me that he had a particular time. He left at 8 in the morning. When did it say he got there? He got there at 3 p.m. So how much time in hours would that be? So sad we've had such a hard time adding today. Okay, from 8 to noon is how many hours? 4. From noon to 3 is 3. So 4 plus 3 is 7. And then we were told how fast he was traveling. We were told that his rate was 50 kilometers per hour. And that's how I knew I needed to get to hours, because my rate label had hours in it. And when I multiply a rate label times the matching time label, then the times go away and you get a distance label. All right, and then we had holiday. And his time was a little different. He left at 10 a.m. but arrived at 3 p.m. So how long did it take him to travel? He was 5 hours. And his rate is the one we don't know. So we're going to use X to represent his rate, because we only have one unknown. So let me draw his little line. So holiday does this. Same route, leaving from the same city, arriving in the same city at the same time. So, of the two possibilities, are the distances the same, or do they add up to equal some distance number given in the problem? Same distance. Now notice, there wasn't a single question or answer number given to us that said a distance label. We had rate labels, we had time labels, but we did not have distance labels. So we couldn't use that second scenario. So now I'm going to put my chart together where we have Jones and Holiday. And across the top is what we're used to with motion: rate, time, distance. But what's different is that rate is 50 for Holiday, 50 for Jones, but X for Holiday. Time was 7 for Jones, but 5 for Holiday. And then to get the distance, the last value, I just do the products. So 50 times 7 equals 350. And then we have 5x. It is this last column that tells me distance, which is what I need for my values in my equation. So I take the distance of one, and I set it equal to the distance of the other. And then I just solve. So it becomes a super simple problem to solve. I just divide, and I get x equals 70. So my answer written out in a sentence is Sergeant Holiday traveled at 70 kilometers per hour. Done. Okay, moving on. Next one. Beth and Mike leave school, traveling in opposite directions. Mike averages 6 kilometers per hour. More than Beth. If they are 18 kilometers apart, after 1.5 hours, what is the rate of each? So on this one, again, the whole point behind the diagram is to help me know whether the two distances are the same or they add up to equal some other distance number given in the problem. So that's why I like to do my chart. So here's the school, and they take off from the same point. We've got Mike going one direction, and we've got Beth going the other direction. Okay, now, a lot of times in these problems, they don't blatantly use the word opposite. What they talk about is north and south, west and east. But those are opposite sets of directions, so that's when we get that idea, okay? So what does it tell us? Let's see, Mike averages 6 kilometers per hour more than Beth. So his rate would have to be more than Beth's. So actually I have to write down Beth's rate first. Well, they don't tell me Beth's rate, so she's going to be X. If he's 6 more than that, how do I write his rate? X plus 6. Further on, it says they're 18 kilometers apart. After 1.5 hours. Now remember, they left at exactly the same time. So both of them have the same time of 1.5 hours. Okay, so looking at that picture, does Mike's distance equal Beth's distance, or do their two distances add up to equal some distance number they gave in the problem? Yeah, notice this word right here. It has a distance label. So it says they're 18 kilometers apart. It's telling the total distance from where Mike is to where Beth is. So this is that situation of D1 plus D2 equals D total. So we'll put our chart together, and we have Beth and Mike. We have rate, we have time, we have distance. So for the rate, we said Beth was going to be X and Mike was going to be more than that. And let's just think logically for a moment. If he is traveling faster than she is, because his rate is 6 more than hers, would he travel the same distance she traveled if they are gone for the same length of time? No, he's going faster, which means he's going to go farther. So that just logically, it couldn't be distance of one equals distance of the other. Yes?
Wouldn't it be Beth, like X plus 6?
Nope.
Because it's
Nope.
Beth has
Nope. Nope. It says Mike averages 6 kilometers more than Beth. Averages is like the equals. So Mike's alone equals 6 more than Beth. Beth plus 6.
Yeah, Beth plus 6. Like,
Yep. Mike is Beth plus 6. Mike equals Beth plus 6. That's how it works. So what we get in the last column is 1.5x and 1.5 times the quantity x plus 6. And it's these values that I'm going to use in this idea here. So I have 1.5x, that's Beth's distance traveled, plus 1.5 times the quantity x plus 6, that's Mike's distance traveled, and that's got to equal that total of 18. Okay? So I'm just going to go ahead. I'm not going to worry about getting rid of decimals. I'm going to just keep them there and work with them. So I get 1.5x plus 1.5x plus, let's see, I get 9.0 or just 9 equals 18. So I'm going to combine up like terms and I'm going to do opposite operations to get all the constants together. And 1.5 and 1.5 gives me a total of 3. X equals 9, and I divide by 3. And I get x equals 3. Well, x represents Beth's rate. Okay? If I want to figure out Mike's rate, I'm going to have to plug that value into what I know about Mike's rate. So if I take his Beth's 3 and add 6 to it, that's going to be Mike's rate. So what I say for my answer is Beth's rate was 3 kilometers per hour. And I knew it was kilometers per hour because they're traveling in hours, is what they told me. And then we also had that label right there, kilometers per hour, comma, and Mike's rate was 9 kilometers per hour. And that's that answer. Okay, next problem. This one has something unique about it. Mark drove his car to a garage at 48 kilometers per hour. And then walked back home at 8 kilometers per hour. The drive took 10 minutes less than the walk home. How far did Mark walk? And for how long? So two questions we have to answer. So again, Mark drove his car to garage at 48 kilometers per hour and then walked back home at 8 kilometers per hour. The drive took 10 minutes less than the walk home. How far did Mark walk and for how long? So two questions that need answering. All right, so I'm going to draw a picture. It says that he walked back home, so I'm assuming that when he drove away, he started at his house. That's what it sounded like. And then he gets to a garage. Now, my assumption is it's like a not a parking garage, but it's one where cars go to get fixed, okay? So there's two parts to his journey. One in which he drove, and then the second of which he walked. Now, just looking at that part of the picture, which of the two possibilities does this look like we're going to be using to write our equation? Are the distances the same, or do the two distances add up to equal some distance number in the problem? So this looks like we're going to go back to D1 equals D2. Okay, so let's write down some information. When he drove, we know what his rate was. It was 48 kilometers per hour. And then when he walked, we knew what his rate was. It was 8 kilometers per hour. And then it says the drive took 10 minutes less than the walk home. And that's where we fall into a problem. According to our rate label, what label does our time have to have? Say it again? Yeah, so we need to have hours, except this one talks about minutes. So what we're going to need to do is to take 10 minutes and figure out what part of an hour it is. So 1 hour is 60 minutes, which equals 1/6 of an hour. All right, now that I have that piece, I can go and deal with time. So it says the drive took 10 minutes less than the walk home. So according to this, the walk home's time was X, and the drive was going to be 10 minutes less, or X minus 1/6. Okay? So I'm going to go ahead and do my chart. We have drove, walked. We have rate, we have time, we have distance. We have 48 for the rate he drove, 8 for the rate he walked. Time for driving was X minus 1/6, and time for walking was X. So the distance for driving would be 48 times the quantity, X minus 1/6, and for the walking it would be 8X. According to this picture, we're going to take those guys in the last column, and they're going to create my equation. So the distance of one equals the distance of the other. And so I'm going to distribute to get rid of parentheses, and I get 48 times x is 48x minus 48 times 1, 6. 6 goes into 48 8 times evenly, equals 8x. Well, I want my constants to go on the right, so I'm going to add 8 to both sides. I want my variables on the left, so I'm going to subtract 8x from both sides. And I get 40x equals 8. I'm going to divide both sides by 40, and I get x equals 8/40, but that simplifies down to 1/5. So what I've just discovered is how long it took him to walk, which is precisely what the question asked me to figure out, is how long would it take for him to walk. So this represents time to walk. So when I write my answer, I'd say how far did Mark walk and for how long? I got the how long real easily. Mark, not marked, walked for 1/5, and what would the label be? What's the label for time? Hours. Okay, we have to have a label for time on a time number. And now how do I figure out how far he walked? Zach?
You can plug the 1/5 into t.
I'm going to take this and he's going to perform double duty. He's going to go into the distance column for walking, and I'm going to multiply that. So I'm going to get 8 times 1/5, which is 8/5, which I'm going to rewrite as a mixed number. So 1 3/5. So Mark walked for 1/5 hours and for a distance of 1 3/5. Whoa, you can't even see that. Let me do that darker and excuse you. Kilometers. Okay, so Mark walked for 1/5 of an hour and for a distance of 1 3/5 kilometers. Now, 3/5 can easily be changed to a decimal, and it would be 1.6 kilometers. You could do that, but I won't tell you to. You have to go one way or the other. You can just leave it. All right, let's see if we can get one more in. And again, it's not so bad to write. I'm picking all the easier ones to write. So let's see, this is, our fourth one. So Cindy begins biking. To the park at 20 kilometers per hour at noon. So we have a rate and we have a start time. Dean leaves from the same point "15 minutes later to catch her." If Dean is biking at 24 kilometers per hour, how long will it take him to catch Cindy? Cindy begins biking to the park at 20 kilometers per hour at noon. Dean leaves from the same point 15 minutes later to catch her. If Dean is biking at 24 kilometers per hour, how long will it take him to catch Cindy? Is it possible for him to catch her? He's traveling faster. So yes, it's always a possibility. So basically, we're starting from some point, and you've got two kids on bikes. This person is going, and what happens is that the second point leaves from the same spot, but it's just he's later. But when he catches her means this. So just from that diagram, D1 equals D2 or D1 plus D2 equals D total? Are those distances the same, or are they going to get added up to equal something else? They're going to be equal to each other. So this is Cindy. And Cindy has a rate of 20 kilometers per hour. And we know time-wise, she leaves at noon. That's all we know. For him, Dean, we know that his rate is 24. And his time is 15 minutes later. So we have the same issue we have in this problem that we had in the other one, is that 15 minutes can't compete with a label that's supposed to be hours. So we're going to convert it to hours, and we get 1/4 of an hour. So I guess you guys are going to have to wait to find out the rest of this. Okay, so in our chart, we're going to have Cindy and Dean. Rate, time, distance. We've got rate for Cindy is 20 and for Dean is 24. Now time, it says that she leaves at noon, but it doesn't give her time. So we're going to let her be X for time. And Dean left 15 minutes later or 1/4 of an hour later. So distance for Cindy is 20x, and for Dean it's going to be 24 times the quantity x minus 1/4. And then you can see that he's going to catch up to her, so the distances they traveled are the same, so we set them equal to each other. They're two distances. And then solve. So we get 24x minus 6 equals 20x. I'm going to add 6 to both sides, subtract 20x from both sides. I get 4x equals 6, divide by 4. And I get, reduce that down by 2, 3/2. Now this represents how long it takes Cindy. So this represents Cindy's time. Okay, so this is representing Cindy's time. But the question asks for how long will it take him. So what we're going to do is take that value we got for Cindy's time and plug it in to Dean's time. So we've got 3/2 minus 1/4 is going to be, I'm going to change this to 6/4 minus 1/4, and the answer is 5/4. Sorry to cram it in there. So if I take that to a mixed number, I'm going to get Dean will take, or Dean takes mixed number 1 1/4 hours to catch Cindy, or catch up with Cindy. And there you go. Good luck.